Welcome and thank you for joining us today for this SPE Tech Talk with TETRA Technologies. I'm Joe Sinnott, your host for this broadcast, which will focus on TETRA Neptune multi-use fluid, a customized, environmentally friendly, cost-effective alternative to expensive cesium formates and regulated zinc brines, which are restricted in the Gulf of Mexico and banned in the North Sea. Today, we are joined by TETRA to explore this unique clear brine fluid and its evolution for use in high-performance water-based drilling and reservoir drill-in fluids. We'll also discuss how advancements in polymer and corrosion control technologies will enable the industry to drill hotter and deeper wells in deep water and ultra-deep water plays. And before we dive into today's conversation, I want to invite you, the audience, to take full advantage of this live broadcast by sharing your questions about today's topic in the comment section on LinkedIn or Energy Stream for a chance that our guest will answer them later on in the show. Two other great ways to interact with the broadcast are: one, to let us know where you are watching from, and two, to answer today's audience poll question, which asks, where could TETRA CS Neptune multi-use fluid technology create value in your asset? A, as an ultra-low solids reservoir drill-in fluid in aqueous or non-aqueous systems. B, as a cost-effective alternative to cesium formate. C, as an environmentally compliant solution to replace zinc-based fluids. D, as an ultra-low solids, high performance water-based mud offering low ECDs and faster ROPs. Or E, none of the above. A lot of things to choose from there for this multi-use fluid. Let us know where you think this fluid could make the biggest impact and add the most value for your asset. That being said, go ahead and add your answer there in the comment section, and our guest will be happy to discuss all of that further, all of these uses as we move through the show. But for now, let's go ahead and actually introduce that guest. And for that, we're going to turn to the Woodlands, Texas, where we are joined by Richard Hay, Global Vice President of Completion Fluids at TETRA. Originally from Aberdeen, Scotland, he has 34 years of experience in the oil and gas and renewable industries, serving in leadership roles in Africa, Asia, Europe, and the Middle East. Richard holds a Bachelor of Science in Chemistry from the Open University in the United Kingdom. With that, Richard, welcome back to SPE Tech Talk.
Yeah, hi, good morning, Joe. It's great to be back and get this opportunity to have this discussion. So thank you.
All right, well, it is our pleasure to have you back here. And as you know, Richard, our audience, they love the details. They love the technology. They love hearing about the latest and greatest. So if you would, can you start things off for our audience by giving an overview, and if not, maybe even a timeline of, how we got to this place where you've got, the ability to apply aqueous chemistry expertise to engineer true and pressurized crystallization temperatures and reservoir clear brine applications. Again, it's a big topic. It's a wordy topic. And if you would, set the stage for us. And ultimately, if you would, maybe touch on how, you can enable zero or ultra low solid fluid opportunities for companies that could definitely benefit from all of this stuff that we're going to dive to here in a mere 30 minutes, Richard.
There's a lot to talk about, but we'll keep it brief and succinct and hopefully interesting, Joe. So thanks for that introduction. So, a bit of background. So, with completing wells, using solid-laden fluids such as oil-based mud, water-based mud, or synthetic-based mud, solids can impair reservoir production and damage the function of downhole completion and DSD tools. So, therefore, completing wells with clear brine fluids is the preferred alternative. Completion brines are typically halide or formate salt solutions in water, but they too also can have some shortcomings. At lower temperatures or increased pressures, these salts in the fluids can crystallize. So this causes potential well control concerns and or costly operational disruptions. Completion of high pressure wells with densities above 14.3 pounds per gallon for calcium bromide or 13.1 pounds per gallon for potassium formate. This historically required the use of brines containing zinc bromide or cesium formates or potassium formates to minimize formation damage. Yet in addition to the demerits that both these fluids have, that are inherent liabilities. For example, with the zinc-based fluids, as you mentioned in the intro, they're restricted. They're classified as a priority marine pollutant, particularly in the North Sea. This is due to the potentially harmful effects on the environment. And they also have a low pH, i.e. they're acid. The zinc-based halides increasing the potential for corrosion of metal components. And obviously there's a risk to personal safety. There are also concerns around handling zinc-based fluids at gathering stations now. This has become more prevalent, with increasing restriction or prohibitions with respect to receiving zinc halides in the processing facilities. With respect to formate fluids, which I have to admit is an excellent technical option in many, many cases. However, there is limited production worldwide. The material comes from only a few sources, very highly localized, and this can restrict supply and lead to higher costs in high volume deep water applications, for example. Moreover, when used as a packer fluid in high temperature, literature suggests, and I reference Javora 2003 paper here, suggests that the formates may cause hydrogen-induced cracking, or HIC, in high temperature wells, in the presence of corrosive gases, which could lead to failure of production tubing. So, in addition to that, other motivations to create a high new density brine can include the increasing number of deep water wells, deep wells in deep water. Again, the limited supply of the source material for formates are an issue. Create an alternative that can achieve other functions, for example. However, getting to a point where a new high-density brine is developed actually required a step change in aqueous chemistry. And as the saying goes, necessity is the mother of all invention. And the genesis for development of this novel aqueous chemistry was when TETRA was approached by a major US operator in the Gulf to develop a novel clear brine fluid. Cesium formate was an issue because there wasn't enough supply for the volume in this deep water well. They requested a properties of 15.4 pound per gallon with a PCT, or a pressurized crystallization temperature of less than 30 degrees Fahrenheit at 15,000 psi. So very, very strict remit, something that can normally only be achieved by expensive formates. So the traditional alternatives from a TCD standpoint were formates or zinc, but they weren't acceptable for toxicity and cost reasons, and inventory wasn't available worldwide to service the volume. So we had a real challenge there to design this novel fluid, especially at the temperatures and the pressurized crystallization temperature was 15,000 psi. So obviously that lowers the TCT in terms of a safety buffer that's required. Very, very demanding. Can you bring up the first slide, please, Joe? Appreciate it. So, the central design philosophy was on engineering a TCT, which, TCT is the crystallization temperature of a brine, and it's not linear. It's a function of dissolved solid salt concentration. And in this graph, you can see there's an inflection point, which is known as the eutectic point in chemistry or physics. And this represents the lowest crystallization temperature achievable with a specific brine chemistry. So if you look at the plot of crystallization temperature versus the brine density, this typically follows for, what you see here typically follows for a calcium chloride and calcium bromide system. But each brine system, as you would imagine, has its own phase diagram. And our objective was to shift the eutectic point to the right using new aqueous chemistry. So as long as the brine density is less than the density at the eutectic point, i.e. to the left of the eutectic point, increases in brine density lower the crystallization temperature. However, in contrast, once you get densities above the density of the eutectic point, i.e. to the right of that graph, it all changes. So for example, at 13.2 pounds per gallon, calcium bromide, the TCT is minus 57 degrees Fahrenheit. However, if you go up to 14.9, again shifting to the right of the eutectic point, the crystallization temperature then rises to 57, so plus 57 degrees Fahrenheit. So obviously that density, fluid is no longer considered viable for many well applications. And again, each brine system has its own phase diagram. So the objective is to shift that eutectic point to the right. So to affect this physical shift, which was an impossibility previously, we developed what's called crystallization suppressant agents. And this was a step change, Joe, in our clear brine fluid aqueous chemistry. It was a step change for the industry. So it enabled us to have higher brine densities at lower TCTs that can be formulated and applied in the field safely without the risk of crystallization, in the wellbore and the pits, etc. So I won't go into too much of the validation work. We've talked about this before. It's available. Come and talk to me, and I can tell you all about the extensive research and development work we did on this. But obviously, the test program included measuring TCTs, PCTs, thermal stability is to 325 degrees F. We've done all the compatibility testing with elastomers, downhole fluids, corrosion, very extensive corrosion testing, environmental testing, hydrate inhibition, shale stability, regain permeability, etc., etc. So a lot of work went into developing this, and we actually achieved this from concept through to having a working system. It was actually just under 3 months. It was quite incredible. It was a lot of focus. There was a very tight timeline for the customer. So very proud that we managed to achieve that. So in terms of the system, developing these novel crystallization agents, which were a step change, enabled us to develop a range of clear brine fluids that cover the density ranges with the required operational TCTs for brines that don't contain zinc or other proprietary pollutants or raw iron formates. So if you could go to the next slide, please, Joe, appreciate it. So here we achieved this goal by developing monovalent and divalent options. And you can see here, looking at the chart, that in the monovalent applications, we can extend densities from 12.3 to 15.4 ppg for the high density monovalent technologies, with thermal stability up to 350 degrees and sometimes a little bit more. For the divalent applications, which is the larger bar chart on the right there, we cover densities through 11.6 through to 17.5 possible, and that's using either calcium chloride or calcium bromide as a stock brine. And again, we can get thermal stability up to 350 degrees Fahrenheit. In terms of the cost, there are a very wide range of costs across the density ranges, as you would expect. However, depending on the well parameters, there can be significant savings made versus, for example, mechanical or alternative brine options. If we're looking at the lower density ranges and in some reservoir drilling fluids, because of the different concentrations of these crystallization suppression agents, that could be remarkably cost effective. Again, it's like all brine fluids. If you have a lower density, the difference in cost can be exponential between a low density and a high density. So it's a very wide range of cost applications. As a footnote, with each valency, monovalent and divalent, the chemistries are interchangeable and fully compatible, and efficiencies can be achieved with hybrids of the systems as well. So we've got various hybrids of the chemistries that can give various cost and technical specifications. Fundamentally, the system is boutique. It's an engineered system. It's all about custom engineering, the cost advantage. There are a number of alternative chemistries in the Neptune multi-use fluid system, and they can be fine-tuned to provide many different scenarios or solutions, both for clear brine fluid options and applications that require zero or ultra-low solids.
Great. Well, if it wasn't already clear to our audience there early on, I think it's abundantly clear now that Richard is a wealth of knowledge on this topic. So, Richard, thank you for setting the stage, talking about the evolution to get to this point. So, again, as a reminder to our audience, we have Richard here live. Ask your questions. Take advantage of his expertise, because that's why we're here on SPE Tech Talk. But for now, Richard, so you brought us up to this point. You talked about, how you got to a certain point in the, the Neptune CS fluid life, if you will. What about what's next? At the intro, we talked about this being a multi-use fluid. So can you shed some light on the evolution of its uses and how we move beyond sort of the foundational stuff that you just shared over the last 10 minutes or so?
Yeah, I'm pleased to, and thanks for calling me a wealth of information. I really appreciate that. So, yeah, so the original design premise was about having ultra low TCTs at higher brine densities. So, as a result, you've got higher density fluids with no or zero solids, and so the value proposition is moving away from having this high dense brine, the low TCTs, to what other applications have been done with zero solids or ultra low solids. And the slide there sort of illustrates some of these, and I'll just touch on them very briefly. So one application we've been working on with an operator in North Sea is using the Neptune brine as the discontinuous phase or brine phase in invert emulsion reservoir drilling fluids or screen running fluids. So with a higher density vis-a-vis a calcium chloride, which is traditionally used, you can get a much higher overall fluid system density with zero or very low solids. That's obviously got applications when it comes to screen running fluids, etc., where you're concerned about solids providing any issues. Typically in these fluids, you formulate them at very low oil-water ratios, typically 40-60. And achieving acceptable fluid stability at such low oil-water ratios is notoriously difficult. Formulating a 40-60 fluid with a commercial 40.2 pound per gallon calcium bromide provides a density 11.2. However, you've replaced that with a Neptune of brine of 17.5 ppg, then you can get a solids-free invert with a much higher density up to 12.9. So obviously clear benefits there. The system can be used in slugs. It has been used in slugs to avoid wet tripping, cost saving obviously there without spilled brine on the drill floor. But also there's HSE benefits as well, so you're not having brine, spilling out on the drill floor and potentially over personnel as well. So another recent development, Joe, has been the engineering of a pad fluid compatible with control line fluids for BOP stacks. One operator in the Gulf of Mexico here had issues with control line fluids forming hazardous emulsions with zinc bromide completion fluids. This has resulted in an inability to flush these from the BOP stack, and an engineered solution would have required a 12 million retrofit to the stack. So TETRA was approached. We were asked to provide a solution, and we designed an extra high density divalent solution at 16.5 ppg, which was proven not to create emulsions or hazard blockages in the subsea stack. And this was recently deployed to the field, successfully applied in the last month. So a major success there. We're also collaborating with a major service company to provide boutique engineered fluids for annular interventions. This is in the early stages. The Neptune system may also have applications in large volume fracking operations, especially at the lower densities where sodium bromide is utilized. We collaborate with a service company and develop a system that would take a standard 12.5 ppg sodium bromide and economically extend it to 13.1 ppg, therefore allowing for a denser fluid column in effect. A denser fluid column, an effect, an effect in a larger hammer to fracture formation. I think we're looking at applications at intermediate sections. I think the technology can be applied in the design of high performance water-based fluids. For an example, in the drilling of highly deviated sections with narrow frac gradients, with a higher starting brine density, much less solids are required. This will and can result in lower PVs, plastic viscosities, better management of resultant ECDs, less sag potential because of lower solids laid in. Plus, there's a buoyancy effect as well with the denser brine, and even potentially improved ROP and more hydraulic horsepower at the bit because there's less solids as well to affect the ROP. There's also applications in wellbore cleanup pills, having a zero solids, higher density push or wash pill, whether it contains wash-up chemicals or it's just viscosified, for pushing out the oil-based mud or other fluid prior to completion. There's opportunities there. And reservoir drilling fluids or drill-in fluids, we see this as a major developmental area, especially with higher pressure and temperature assets being developed across the world. We believe the Neptune technology offers unique advantages and can be used either as a base brine for a water-based drilling fluid, or as the discontinuous brine phase in an invert-based drilling fluid. Obviously offers a significant reduction in solids loading, enabling ultra-low solids concentrations. This allows for minimum solids required for bridging the pore throats, which is essential in forming a thin, non-damaging filter cake, and possibly also allow for higher rates of penetrations due to the reduced solids. So just an example of sort of the solids loading reduction, sodium potassium formate brines, which are used as base brines for reservoir drilling fluids. Sodium bromide is typically limited to 12.3 ppg and potassium formate to 13.1. When the fluid is formulated with, say, an optimal 50 pounds per barrel of ground marble as a weight and bridging agent, an overall density of 13 ppg can be achieved with sodium bromide as a base brine, and a slightly higher density can be achieved with potassium formate, say up to 30.7. However, when higher density is required, more solids must be added, increasing the risk of formation damage. With the use of the higher density Neptune monovalent brine, 15.7 ppg, for example, that means we can have, if we add 50 pounds per barrel ground marble, then we can get a density of 15.8 with the same solids loading versus 13 ppg with a standard sodium bromide brine. I won't go into too much details on the formulations, but we've got excellent rheological profiles in a monovalent solution at 120F, excellent 72-hour static aging at 250 degrees F, flat rheologies, low PVs, excellent rheological profiles across the board. And we've got ongoing work to see if we can extend that temperature stability beyond 300 degrees F. Quickly on our divalent offerings, this is a lot more tricky. Unlike monovalent, divalent systems are very difficult to get a rheological profile with acceptable filtration properties. However, TETRA recently have developed a novel technology that's a natural starch that gives us acceptable yield, great rheological profile across the rheology range, and it's a starch that breaks down as well and doesn't leave any damaging material now near wellbore. Unlike synthetic polymers, which are typically used in divalent brines, they can be very damaging to reservoirs and very difficult to remove. These natural polymers, they perform very well up to 280 degrees F, excellent yield point and PV properties, low-end performance, 63 readings in gels, and excellent static agent at 280 F. So just very quickly on, the sort of example of reductions in solid loading using a divalent Neptune system. If we start off, if you want a 15.6 ppg drilling fluid and you start with a 14.2 pound per gallon standard calcium bromide, you require 158.2 pounds per barrel of calcium carbonate. If you start with a 15 pound per gallon Neptune, then that reduces down to 76.2. If you look at formulating a 16.5 pound per gallon drilling fluid, using a 14.2 pound per gallon, you'll need 260 pounds of calcium carbonate. Whereas if you go with a 15 pound per gallon Neptune, then using alternative solids, you can get down to 85.3. So clearly a value proposition there and enabling much less solids to be reused. So key to designing a reservoir drilling fluid is a PSD of the bridging material as a particle size distribution. This is essential so the fluid loss is minimized to the near and far wellbore. You don't want any damaging solids migrating into formation or developing damaging fines. With a higher brine density with Neptune, as stated, the solids loading can be remarkably reduced, and that allows you to better engineer a particle distribution profile to bridge your formation pores throats, whether this is using the idle packing theory, the 2/3 rule, or the Abraham's model. The system is also highly inhibitive shale, so if you have any mobile, dispersible, or otherwise reactive clay mineralogy in your formation, then the Neptune can inhibit that. And there's been extensive testing done in return perms at third parties, so we typically see 95% plus return perm. The fluid can also be converted to maybe a screen running fluid or a packer fluid as well, so you get two systems for the price of one. Thanks, Joe.
Well, I'll be honest. I think at some point, Richard, I started to lose track of the versatile options and applicability and the uses of this fluid. At some point, I was actually wondering, are you going to get to the point where you're going to tell me it's going to wind up in my grocery store someday, and I'm going to be able to drink it?
Well, it's not going to end up in Walmart, Joe. It's not. We don't plan to sell it there. So,
but in all seriousness, one application that obviously we talked about at the intro, and I love just some quick thoughts on is of course the sexiness of deep water, ultra deep water applications, deeper, hotter. You mentioned obviously higher temperatures a bit in some of your comments already, but any quick comments about how this fluid is going to help meet the needs of those deeper, hotter wells?
Yeah, well, thanks, Joe. So I touched on the polymer. This we have a novel polymer.
Sure.
It's new to the industry. It's natural, so it will degrade, especially at temperature. But it'll be able to formulate a solid, thin, permeable filter cake. So I won't go into too much detail about that. But we identified that as we're drilling deeper and hotter wells, especially in the Gulf of Mexico here, there's a gap, there's a technological gap in the industry's requirements. And we've been working over the last 24 months on high temperature corrosion inhibitors. It's a real issue, especially as you drill above 280 degrees F. And like I say, we've been working on the last 24 months on new technology. We've actually developed we've got a patent pending on a novel chemistry that's never been hitherto used in the industry at the moment. This provides corrosion rates at 300 degrees F of less than 0.1 mils per year. This is versus around 14 to 15 mils per year you get with a standard 14.2 brine. Yeah, the very high temperatures, say 400 degrees Fahrenheit, we get corrosion rates less than 5. So it's quite incredible. So we're very excited about this. The obvious value proposition to the customer is, one, it's reducing well construction cost. It may even reduce the need for some exotic metal tubulars. It definitely improves asset life, whether it's used, particularly in annular intervention solutions. And also it's environmentally friendly. There's no raw material constraints. So one thing I'd just like to touch on lastly, Joe, is, what's often overlooked and is not widely understood in the industry is just how important the quality of the brine itself is. Impurities in brine can markedly increase the corrosion potential, whether it's localized pitting or environmental stress cracking. TETRA, we manufacture our bromides from elemental bromine, not salt deposits or waste bromine streams. So plus this results in very low chlorides in the order of 50 ppm, which is standard in our manufactured brines. And in fact, some of our other brines, we manufacture electrolyte bromides for the energy storage industry. We can manufacture bromides with impurity levels measured in parts per billion. So this is a specification. This is attributed to the manufacturing process using elemental bromine. So all these factors have a huge impact on stress and environmental corrosion. The concentrations of chloride, the impurity levels, as well as, and we believe we've got a great solution for the industry with our stock brines that are very low impurities and this novel inhibition chemistry. And they can be applied in completion fluids, barrier fluids, packer suspension, screen running, or any other brine-based applications. So that's where we are, Joe. Thank you.
Well, thank you for sharing that. What I want to do now here, we only got a little bit of time left, but I want to bring up the poll question from earlier. I'm not going to read through all the answers because I think you probably doubled or tripled the potential options for this fluid and how it could be applied. I know we got I think maybe the top answer so far was on using it as a drill-in fluid, and we actually have a number of questions, Richard, that speak to some questions around drill-in fluid. Several of them involve filter cakes. So they're talking about, all right, the removal, what do they look like? Can you shed any quick insights here? Again, I know we're up on time, but since that seemed to draw the attention of people, and we got a couple questions related to what you're actually seeing, curious if you can comment on that at all.
Yeah, so we typically get, I'm looking at the questions here on the right-hand side. So, what's really important. So there's different models in how you engineer your particle size distribution, and that's very important. And it's important as well to use different models and a variety of ceramic discs or pore throat sizes when you're modeling this, because typically in a reservoir there's a wide range of pore size distribution, typically we aim for a filter cake that's 2 mils or less, obviously not fluffy. In our initial screening we use what's called a PPT or a PPA apparatus, where you can have different temperatures and pressures and apply a filter cake across a ceramic or a simulated core disc. And one of the main screening techniques is to look for design parameters, is to look for a very, very low or zero spurt loss and a very low overall total filtrate loss. So that's what we focus on. And obviously, when it comes to testing beyond the sort of PPT, there's various there's core flooding, there's also pressure liftoffs. We look at having pressure liftoff pressures of 3 to 5 psi, which is typical of what some major operators look at.
Great. All right. Well, thank you for that answer. Thank you, of course, to the various questions that came in on that particular topic. Again, unfortunately, I don't think we're going to be able to get to all of our questions. So let me turn it back to you. So again, we got a lot of interest in this topic. Richard, you laid out a lot of technical details that I think, probably get a lot of people excited about this, whether they're watching live right now or on demand later. So let me ask you this. What else do you think our audience needs to know here as we move to conclusion? What else do you want to share and make sure that they
Tetra's here. Tetra's only here because we have customers, right? And we're very proud of being technically led. We have an excellent team, R&D and development team up here in Conroe. It's called a Technology Innovation Group, and we're here to help you. So we pride ourselves on bringing solutions, real world solutions that have real world value creation for our customers. So if you have any needs, whether you're a customer or if you're a student watching or anyone else, please holler out to us. Contact details are going to come up shortly. I'm on LinkedIn and I'm available to help anyone that has an issue or any questions or any concerns. Just please get in contact with us. That's what we're here for.
All right. Well, I like that invitation. Anyone, if you're walking through your grocery store and you happen to see this Neptune fluid there on the shelves, again, you know how to contact. So as Richard just said, take advantage of LinkedIn there, reach out. And again, anything else, Richard? That's all great. I want to emphasize that.
Joe, I think I'm 3 minutes over schedule, so that's not too bad. I appreciate that additional 3 minutes.
Well, again, no doubt that we could have continued for hours here. Again, I do appreciate everybody that's engaged and asked questions. Keep the conversation going. Certainly, if you're on LinkedIn here, you can keep on adding your comments even after we sign off. So please keep those questions and comments.
Please reach out. Please reach out. I'm here. So we're here for you. So.
All right. Well, that being said, Richard, thank you sincerely for everything you've shared today. Certainly want to give a big thank you to TETRA for helping to make this broadcast possible and helping to share some novel tech for high performance water-based drilling and drill-in fluids. If anyone out there would like to watch a replay of this broadcast, you can do so by heading over to the SPE Energy Stream, the industry's digital pulse. Visit streaming.spe.org. I'm your host, Joe Sinnott. Join us again next time right here on SPE Tech Talk.
Don't miss a moment of any of the great SPE LinkedIn Live events. From the event page, click Attend and Add to Calendar for notification reminders when an SPE LinkedIn Live event is ready to begin. SPE Lives, Tech Talks, Get to Know series, and more. Remember, click Attend on LinkedIn.
In a rapidly evolving energy industry, you need to stay ahead of the curve with relevant content available when and where it's convenient for you. You need the upgraded SPE Energy Stream, the global platform for high-quality content with the energy industry. Fuel your energy career with Energy Stream's sleek new look and easy access to top-quality technical solutions, insights and innovations, trending topics, thought leadership, market outlooks, and education. From original programs to exclusive SPE event highlights, this exciting, easy-to-navigate platform features insightful content delivered live and on demand. Explore insights from industry thought leaders. Then save the videos that interest you and watch them at your convenience. Be at the forefront of energy knowledge and explore the newly updated SPE Energy Stream now.